Now we're ready for the third link using the inertial frame, again, simply the IJK. So we're looking to, pull it up here, we're looking to explore this link here. So again, we're going to use the kinematics table. On each kinematics table, as we've seen before, we have a diagram that I have here on the upper left that lets us focus just on the link we're looking for. And again, that is link 3, which is from Q to capital R. Again, using the nomenclature, that original point was B for base, P for point, and then we just let it from there. So I is to the right, and J is up. So again, we're not using much of the table, and as I've said, I believe in each of these review videos, we're really only concerned with 5 lines. We're concerned with these 3 worksheet ones here, the velocity at Q and the acceleration at Q. And once again, I hit a dead spot on my screen. Here we go. And we're doing this, so if I add up these 3 lines here, I get the full velocity at capital R, otherwise known as velocity R with respect to some sort of fixed inertial origin. If I add up these 5 lines at the bottom, I get the full acceleration of R, or acceleration R with respect to, let's say, O. And again, these are vectors. So because this is simply the inertial frame, a lot of this is actually very easy, right? These are still 0. We'll be using them later. And as I said in the other videos, just remember this top line is the angular velocity of the coordinate system. The second line is actually alpha. It might not look that way. Angular acceleration of the system. The next one is my displacement vector. So it is starting at, let me pick a different color. It's starting at Q and going to R. So this vector right here is typically either called R from Q to capital R, or in dynamic notations, usually capital R with respect to Q. It means exactly the same thing. So nothing has changed. If we've done a good job setting up everything the same way, it should look easy. It should start looking really repetitive, which is a good thing when you're trying to do well in a class. So it's R3 cosine psi, R3 sine psi, and 0. Again, right, because it's R of R slash Q is R3 cosine psi I plus R3 sine psi J plus 0K. And we're just sticking it into a table where I already have my unit vectors I, J, and K out here. Okay. So now what is VQ? Well, if you remember, that is from the table before. So I rewrote that here to the right, what we had in the last video. And so I have here my VQ, and then later on my acceleration at Q. So rather than rewriting things over and over again, I traditionally would just circle it so it's really clear what I'm looking for. And I'm going to name this VQ scalar, right? No vector because the I is on the outside of X. This I'm going to call VQY. Again, it's a scalar because, right, the J is right there. And similarly, when I'm ready for it, down here, that's equal to, that spot again, that's equal to AQ in the X direction. And this term here we found before is AQ in the Y. So becomes a bookkeeping exercise. Let me zoom in here a little bit. So this is VQX, so just that stuff we just had. This is VQY. This is AQX, and this is AQY. Because we're using inertial, omegas and alphas is 0, so these cross products here are 0. We'll do body fixed in another review. Depending on when you're watching this, you might have already done in class. So there's no alphas. Oh, that spot again. There's no omegas. So these are 0. So at this point, it's just mindless math, and as I've said in past videos, it lends itself to being automated. We've done all the real work, and now it's just a derivative. So when I look at this first open line here, this line right here, it's velocity of r with respect to q, right, or r dot r with respect to q. So I just need to look at here and take the time derivative. So right now, r3 is constant, which keeps it simple. Later on, I'll do a review where r3 can change in length, just more stuff to write. So what do we have? The derivative with respect to time, I need to use the chain rule because psi is a function of time, but there's no t there. So I take the derivative with respect to psi, and then psi with respect to time, which is just, as we've seen before, just psi dot. So I'm going to end up with minus r3 psi dot sine psi r3 psi dot cosine psi and 0, and those terms should look exactly like what we have here and here because I defined my theta, phis, and psis all from the y-axis. You could mix it up, but I didn't. It makes everything easier to check. And similarly, to get this line here, I'm just going to, again, look at this line here. So I'm looking at my velocity line to take the derivative. I'm not going to overwhelm myself by looking at too much. It allows me to focus. So I have how many functions of time here? So r, we says constant for right now. That's a function of time. Psi dot, that'll give me a psi double dot. And again, my psi, I need to take a derivative of. And similarly here, I have two functions of time. So if you remember back to your important math classes, I'm going to get two terms for my acceleration. So what do I have? Try to squeeze in here. It'll look like what we've done in the past. R3. If I hold sine psi constant, I have psi double dot sine psi. So psi double dot is my angular acceleration with respect to that particular angle psi. Its units will be radians per second squared, radians per hour squared, whatever it is, but it has to be radians, not degrees, not RPM kind of thing. Or RPM would be angular velocity. You'd have to convert it over. Now, if I hold the psi dot constant, so I'd have my minus R3 psi dot, derivative of sine psi, use the chain rule, is what? Cosine psi times a psi dot. So that becomes squared cosine psi. Similarly here, I need the product rule and the chain rule. If I hold cosine psi constant first, R3 psi double dot cosine psi minus R3 psi dot, and derivative of cosine psi is minus, I already have the minus here, and then it's a psi dot, sine psi times a psi dot, so that squares. So all of this together, if I need it later, and I will, when I'm doing constraints, got to get out of these dead spots, is acceleration of capital R in the x direction, that's my scalar value. This is equal to ARY. Again, this don't have anything here, but this would be ARZ. Similarly, all of this equals VRX, and all of this equals VRY. And we're going to use that in the next video for constraints to get our 4-bar mechanism. So again, hopefully we have the same pattern, but what have we done? We've done a triple pendulum to find the velocities and accelerations if needed at capital R.